Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in the previous module we were discussing the moments acting upon a system of particles, and we will continue our discussion, especially finding the geometric meaning of the moments that we found, and especially we will try to answer what is the direction of the moments acting on the particle under consideration. So what we were discussing were, so let's recap. So we were looking at moments, So moments, or we call this as moment of force sometimes. So moment of force, and we were looking at the geometric interpretation. And what we saw was that suppose we have a particle P on which we have to find the moment, and let's say we have an axis given by let's say along the axis, some axis, and let us name the axis CD, right? And let us say that there is a perpendicular distance, the distance of the particle under consideration from the axis is r, and all we care about is not this distance r, but the perpendicular distance of this particle from the axis of rotation. So let's say the perpendicular p, small p, makes an angle alpha with the axis of rotation, and which means that this p is nothing but r cos alpha based on the diagram. So and this is my 90 degrees. Okay. So then we can write down, so recall that the moments, we are trying to find the moments acting upon a system of particles, where we wrote down this expression taking one of the particle as the reference particle. Okay, so we saw that, let's say that particle which is the reference is capital A, and then we found out that with respect to O being the origin of the system or the lab frame, so we have Ka, the moment about a particle A, which is the reference particle, is Ko minus A cross F, where my A is the distance of, so this is the position of P from CD, the position of P from CD from the axis, the position of the particle A from CD, the axis CD. And then what we have is the force which is acting on the particle. This is trying to push the particle or allow the particle to rotate, right? So this force is going to act in such a way that it allows the particle to rotate about the axis. So then we can check that when so this is the formula for Ka. So now coming back, as I'm trying to highlight the geometric interpretation, our Ko, the moment about the origin of the frame, Ko, is going to be F r cos alpha times n, where n is going to be the perpendicular direction. So Well, we see that KO is R cross F. That's the formula here. And where R cross F, so when we take the geometrically, this formula implies that we are taking F, which is the force, the magnitude of the force which is acting on the particle or the couple, times the perpendicular distance R cross alpha, so which is P, times the direction of this moment is going to be n hat, which is perpendicular to both, perpendicular to the plane containing both the vectors R and F, right? So it is, if we use the right hand rule, then we just have to align our four fingers first along the R direction and then along the F direction, and our thumb is going to point along the direction where the moment is acting, right? So that is our n hat. So we find it using the right hand rule. Okay. So then what we have is F. So we have F is this quantity is the magnitude of the force. Okay. So similarly, we can write down this. So this is the formula for one particle. We can similarly write down for a system of particles. So K0 for a system is going to be summation over all such particles I1 to n, and summation Fi, Pi, and n being again the normal, right? And we can use plus and minus. We don't know whether the forces are acting in clockwise, anti-clockwise, or clockwise direction. So accordingly, the plus and minus will be taken care of. So just to give you another perspective of this setup. So moments, what we saw was the moment of force about an axis, moment of force about an axis, and we see that we have direction n, and we have the direction, well, so suppose the particle is P under consideration, n being the eventual direction of the moment, and let's say our force is, as we just saw, force is acting along in such a way that it's allowing the particle to rotate, and we see that this is our angle alpha, and so if this is our this position of point P or particle P from the origin, then let us say rho being the perpendicular distance of the particle P from the axis of rotation, and then let's say phi is the tangential direction, and rho being the radial direction. Okay, so we saw that the couple or the moment of force k naught times n, that is we are trying to write down the magnitude, is going to be R cross F dot with n, and we see that using our standard formulas for scalar triple product, we see that this is R cross n dot with F, and this is also equal to R sine alpha phi hat dot with F. So that's my R cross n, R sine alpha. So this is R sine alpha is going to be, so R sine alpha in this diagram is the perpendicular. So this quantity is R sine alpha. So it all depends how we draw the diagram. So in this case, this is R sine alpha. So this is going to be rho times F dot with phi hat, right? So so that is where that is the value of this couple, the magnitude. So just to give you a bit more idea, this f dot phi is nothing but the azimuthal component of f. Azimuthal component of f. Okay, so then let us now look at an example. So let f be 2I minus j minus 2k. It acts on, we are just looking at an example as to how to calculate such moment of force. So we are given a force in 3D space acting on a particle at P with position vector 0, 3, minus 1, and we find the moment of F about the origin O and about the point A being minus 2, 4, minus 3. Okay, and we also want to find, so the first part is find the moment of F. We want to find the couple K0, and also we need to find the moment of F, the force acting F, about an axis through O in the direction vector 3I minus 4k. Okay, so what we have is, so we want to find the moment of F about the origin O. So moment of F about the origin O. So we need to find the position vector of the particle with respect to the origin and take a cross product with the force. So that is easy. And also we want to and about the second point A. So in the second part of the problem, we have to use that formula for Ka, and also we need to find the moment about an axis in along this direction vector. So let us see what we have to find. So the first part, which is this quantity moment of force about the origin, that is going to be nothing but Ko, and Ko is Rp cross F, where Rp is the position vector, which is nothing but the position vector of P, which is 0I plus 3j minus k, right? And then when we take a cross product, we'll get the answer. So that's the answer. And then the second part of the problem is we have to find Ka. Ka is going to be Ko. With the formula we can quickly substitute. It is going to be Ko minus A cross F. So A is going to be the position vector of the point capital A. We have to, so that is our point capital A is the reference point, and again this is going to be minus 2I plus 4j minus 3k. Okay, so then the last part of the problem says we need to find the moment about an axis through O in the direction vector this. So we need to find the reference, the moment about the origin, Ko dot n. So n is the direction vector which is given to be along the direction 3I minus 4k, and so we can find n to be the unit vector. So this is going to be 3I minus 4k by 5, and then we take the cross product with the dot product with the first part, and we'll get the answer. Okay, so listeners are asked to do all these algebras associated. Okay, so then we can continue. We can look at more examples. Here is one interesting example under consideration. The problem says the system S moves under uniform gravity, a system moves under uniform gravity, show that the total moment of gravity, forces about any point is the same as if all the mass of S were concentrated at its center of mass, center of mass. Okay. So the problem says the system is acted upon by only gravity, and we have to show that the total moment of gravity about any point is the same as if the complete mass is acting upon at its center of mass. So what exactly it is asking? Let us try and find out the moment of force, right, or the moment. So the moment in such a case is going to be k naught is going to be well, we have a system of particles, so we have some axis under consideration, let's say O, with the origin O, and we are looking at one particle with position vector Ri, let's say particle Pi, and so that moment will be Ri cross well, the particle is Pi, and then what is the only force that is acting on particle Pi will be its own weight. So this is going to be mg, mig, and this is acting upon the k direction with a minus sign, minus being downward vertical. So what we have, Ri cross with minus mg or mig times k, right? And we sum up the contribution from all particles I from 1 to n, and what we see is that this is going to be negative MIRI cross with G times K, right? So I is from 1 to n. Okay, so what we have is, so this is going to be, we can now process this information, this formula a little bit. We can introduce the formula for center of mass here. So summation MIRI is summation MI Ri times, well, this quantity can be written as is going to be capital M, where capital M is the summation of all masses, times R being the center of mass, so R is going to be defined as summation Mi Ri divided by capital M. So M times R, and well, of course, with a minus sign cross G K hat. Okay. Now we can certainly choose our axis or our origin such that it lies on the center of mass. So we choose our origin, such that R is 0. So our center of mass is at the origin, which means that what we get is this couple is 0, and which means that the net couple acting on the system of particles is going to be 0, which means that the total moment is the same as if all its mass were acting at its center of mass. So the couple at the center of mass is 0, and we see that the total moment acting on the system of particle is 0. So this is the case when only the weight is the force acting on the particles. Okay, so then let us look at, we need to define what is angular momentum. We haven't come up with a formal definition. So let us now do that at this point. Angular momentum. So definition of angular momentum about a point. So suppose a particle P of mass m has a position vector R, and velocity v. So then, so we are given the details are, we are given the mass, we are given the position vector. We have already fixed our reference frame with some origin O. From that reference frame, we are measuring the position and the velocity. So then the angular momentum, let me call this short notation as AM. The angular momentum of P about O is going to be our this definition L naught is R cross mv, and this for a system of particles. Let's say we have n particles. So for a system of n particles, we find that the moment of individual particles is L naught summation Ri cross Mi Vi. Okay, so we have, this is our sum of individual contributions. So then we can extend this. So this is the angular momentum about the origin. We have fixed some origin, so that is our origin. And similarly, we can define by, let's say, fixing the origin at one of the particle, at the position vector of one of the particle, and that contribution will be negated. And we can similarly have quantity La, which is Lo minus a. Well, so let me write down the step in between. So this is going to be summation Ri minus A times cross with Mi Vi, and we can write this as Lo minus A cross P, or A cross P means the minus the contribution of the particle which is taken as the reference, where P is the linear momentum. It's not something else. So it's the linear momentum of the particle P, of the reference particle. Okay, reference particle. Okay, so that is what we have. Let us look at a quick example. So we have, let's say, the position vector of P of mass m at time t is given by x is a theta square, y is 2a theta, and z is 0, where theta is our degree of freedom. So theta is our variable. Theta is theta of t, where t is the time independent variable. So we need to find the angular momentum. So find the AM, angular momentum of P about the point B, which is given to be a comma 0 at time t. So it seems the problem seems to be quite straightforward. We are given a reference point, and we need to find the angular momentum of this particle whose position vector is given by this formula here, x, y, z, and we need to find LB. So we need not find LO, we need not find the angular momentum about the origin, but about the reference point B. So we need to find LB here. So LB is going to be R minus B cross MV, and this is going to be minus 2MA square theta square plus 1 theta dot k hat. Okay. So what we get is We can plug in. I have already plugged in all the formula, and that is what we get, right? Okay, so then we can also similarly define angular momentum about an axis, right? So angular momentum about an axis. So essentially, we project our formula of angular momentum about the axis we are talking. So so that is going to be about an axis. As I just said, it's a projection. The angular momentum axis is a projection, so it will be a scalar quantity. So the scalar will be L naught dot with n, and this is going to be the component of L naught dot n, and again n is the axis, the rotational axis, right? And we see that this is going to be m times rho times v dot phi hat. So m rho v dot phi hat, and our rho is going to be the perpendicular distance of P from the axis. Rho being, again, it's the same diagram that we have just seen few minutes back, with rho being the perpendicular distance from the axis. Okay, so then what we see is, let's look at an example related to this definition here, or this formula. So the problem says a particle of mass m slides on the inside surface of an axially symmetric bowl, right? The particle slides on the inside of an axially symmetric bowl means that we are given a hemisphere where the particle is sliding. Okay, so then we need to find the angular momentum and also the total energy of the particle, about its axis of symmetry. So with the statement of this problem, I think the diagram should be fairly clear. We are given a hemisphere where the particle is sliding, and the axis of symmetry of the hemisphere is passing through this radius of the hemisphere. And of course, we are here, let's say, so all these, let's say, the tangential direction of the particle is, let's say, given by k hat, and the radial direction is given by rho hat, and we have the tangential velocity is given by v phi. Okay, so we can immediately write down the velocity of this such a particle. V has two components, v rho and v phi. So rho being the radial, phi being the tangential component of the velocity, and we can see that the angular momentum about, let's say, we just want to find the axial component of the angular momentum. L naught k is m rho v dot phi hat, and this is going to be phi hat being the tangential direction. So we see that this is going to be m rho v phi, but v phi is nothing but rho times phi dot. So this is m rho v phi is rho times phi dot. So our axial component is m rho square phi dot. So that's our axial component, and we see that our v rho, the radial component, is going to be rho, using our the Newton's second law. We write it in the polar coordinates. So this is rho dot rho hat plus this is going to be rho phi dot phi hat. Okay, that is what we saw. Okay, so then suppose I'm not going to write the equation of the hemisphere, so we need the equation of the hemisphere in order to write the potential energy. So let us say we already know that. That's fairly easy to write. So let us say that the equation of the bowl is Z is f of rho, and our Z dot is f prime rho of rho dot. So Z dot is this, and we see that. So what is Z? So Z again. So I need to draw Z. So Z is the vertical distance at any given point of time when the particle is present. The vertical distance from the base of the hemisphere, right? So I am writing the formula of the bowl, the hemisphere. So I have some relation of the vertical distance with respect to the radial distance. Okay, so then I can write down my total energy. See, my angular momentum is already found. So all I am trying to find is the total energy of the particle. So total energy is going to be the kinetic energy plus the potential energy, and this is going to be equal to half m rho dot square plus f prime rho dot f prime rho dot square. So this is my kinetic energy component, and plus so this is Z dot. Hold on. Let me write down the complete expression and then it will be easier. So half m rho phi dot square, right? And so this quantity here which I am circling is the kinetic energy component, and the remaining part is the potential energy, because that is what we have. Okay, so then similarly we can write down the angular momentum of, since we have already found the angular momentum of a system of particle, through that formula we can write down the angular momentum of a rigid body. So angular momentum of a rigid body, right? So we see, let us say we consider a rigid body with angular momentum or angular velocity omega, right, about a fixed axis, and let us say we have our degrees of freedom given by theta, and n is the axis that we are talking about, and then our angular momentum about this axis is going to be L naught dot n, and this can be written as the sum of the individual components L0 at I dot n, and this is going to be, this is going to be a scalar where I is the sum of all the particles, and then we can write down the individual formulas. So this L naught I will be mi pi being the perpendicular distance from the axis of rotation, and vi dot with phi hat being the tangential component, the tangential direction. So since we are talking about rigid body, so since body is rigid, we can very well write v I phi, which is this component here, to be omega times pi, right? So it's a rolling condition, there is no slippage. So omega times pi, not exactly rolling and slippage here. So we are talking about the exact kinematic condition here. So we can write down v, the translational tangential velocity, to be related to the angular velocity omega as follows. and this is going to be summation mi pi square omega, right? We can immediately see that this quantity which is summed up is nothing but the moment of inertia times omega. Okay, so what we find is that the angular momentum is the moment of inertia about the axis under consideration times the angular velocity, right? So that's how close the relation is with regards to the linear momentum. So that's where we stop our discussion in this module, and in the next module we'll continue with some examples related to what we have seen in this theory of angular momentum. So thanks so far for listening.